units of executions within that particular process. And it necessarily doesn't mean that those processes came out from a parent process. The thread can be within a Sprout process. So let me see if I'll get an example for you. So when you execute a program in a computer system, the program is working all right. So you have other logics in there that are also running to make sure that the solution that the user is requesting for is given out for the person. So when that happens, there are sub units or lightweight processes that are being executed to aid the main one to accomplish its work. So assuming that you want to, let's say, find the average of two numbers, the first thing that a process, or let me say a thread, will have to calculate for the sum of all the numbers. And then another thread will have to sort of count the total number of numbers you have. So as you want to add up, find the average of your ages, right? So one thread can be executed to sum up all the numbers, whilst another one is also trying to count the individual values that we have, right? And as that is going on, there's another thread which probably is not executing, but it is waiting for the results from both two threads that are running to be able to now perform the division for it. So we can assume that the whole process is called find average. But then within the find average, we have other smaller executions like adding all the numbers together or finding the total number of, values that we have within the set that we are finding the value from. And then when all of these ones execute, they give the result to another function, which will now find the average for us. However, in the whole process, the function is find average. But the other lightweight information that are being run to get at the average were the processes that we are talking about. And those ones can be called as threads because they are executed out of a bigger function like find. Please, are we clear? All right. Now, when we talk about the spawning, in this sense, what we mean is that when you execute the program, the program you executed will explicitly execute another instruction so that it will probably rely on that instruction to finally make a decision, or the other instruction will have to communicate to some peripheral device to make sure that the information that the application you initiated gets the information that you want. So I think one person was giving an example as when you open Microsoft Word these days, they have the autosave over there. So as soon as you open and you begin to write, another process will now be spawned and then start saving at every interval, right? And then also if you go to one of the insert tab, you want to insert an equation, another process will also be initiated in that process or within the process that you have initiated, so that you'll be able to work more efficiently or seamlessly, as if the instructions that you are giving are not independent of themselves, but then they are all independent because one is saving and the other is also processing your information for you. So in technical terms, we could say that threads are quite faster compared to the spawning that we have. And we said earlier that a spawn process depends on the parent process to be able to more like execute or take up memory space. So when you execute a process, the span process will depend on the parent. So if the parent process is switched off, the span one will also switch off. Please, are we getting it over here?
Yes, sir.
All right. And one, I don't know, Emmanuel, you asked about the generations of computers. So when we are talking
Yes, sir.
about major changes in OSs, and when you talk about the operating system that are, I mean, when you refer to machines, so those 8th gen, 5th gen, 7th gen are more related to the processes that we have in the systems and not the operating system. I don't know if you
Oh,
get what
okay.
I'm saying.
Yes, sir. Yes, sir. I get
Yes.
it. Okay.
But then one thing you have to notice that if you have an 8th gen CPU, you might not be able to run it efficiently on an older version of operating system. That is why
Oh,
previously
okay.
we never had an Android operating system, but these days we have them, which are optimized to run on mobile devices. But then we didn't have operating system that run on mobile devices because most of the Windows that we have earlier runs on only PCs. So the 8th gen are mostly related to the CPUs that we have. And they are somehow related to the OS as well. I don't know, recently Microsoft said they've stopped support for Windows 10. So which basically means that they will not patch security issues when it comes up. And that means that when, what should I say, these new operating systems or these new machines that are coming are more going to be compatible to Windows 11 compared to Windows 10. Because these companies work together to make sure that the operating system is suitable for this CPU platform that they are running. That is why it's difficult to run Windows on Mac, unless maybe you do some other tricks, change some variables to make sure to run. But then you can't directly run Windows operating system on Mac device. It won't work that way. So the operating systems, as they upgrade, their upgrade is in line with also the CPU upgrade to make sure they work seamlessly. Is it clear?
Very well, sir. Well understood.
All right. If there are no questions, let's talk about memory management in the operating system. And just as all of us manage our memories, it is very important that those who develop the operating system also make sure we manage or they manage our computing memory for us so that we don't run into deadlock issues or memory not sufficient to have memory on our devices. And this is what you're supposed to do for today: memory abstraction, memory spaces, virtual memory, page replacement algorithms, and some memory segmentations. And then we are done for today. So what is actually a memory? I mean, who can help us understand what a memory is? Anybody? In social science terms, what is a memory? Nobody. Okay. Clifford, memory.
So I would say a memory is a device that holds data or information temporarily or permanently for immediate and then future use.
All right, this is very extensive. GIWU.
That is
Is it
the
GIWU?
brain's ability. That's it.
Yeah, we can hear you.
Uh, I also say that the brain's ability to store, retain, and recall information.
All right, thank you so much. So all that you said is very, very accurate and correct. So that is what memory is all about. Um, where we can collect data in a specific format. I mean, the format is very much important. And then when you move further in this studies, you come to understand data structures like the linked list, the arrays, and I'm very sure some of you, those who are programmers, understand what I'm talking about, the graphs, the heap, and the rest. So a memory is actually a term that defines a collection of data, not just a collection of data, but then we have to understand that the data is in a specific format. And also the memory helps us to store instructions and process data as well as you just said. And since we are talking about operating systems, our focus is going to be on the main memory because that is ideally where the operating system mostly resides when the computer is in operation. And equally, you can see that the memory also comprises of an array or group of words or bytes, with each of them having their own location. All right, and then the main memory is one of the large array or bytes, as I said earlier, which range from hundreds of thousands to billions. And the main memory also is a placeholder, or let's say a repository for rapidly available information that are shared by the CPU, input-output devices, and the operating system. So that is what the main memory basically does. It holds information that a CPU can actually reach out for, and the input output devices, and also the operating system as well. So that is the main memory. And then also it is the place where programs and information are kept when the processor is effectively using them. So if the processor is idle, it literally means that there are no data, there are no information on the memory, right? And ideally, when we talk about the memory, our main focus is on the RAM. And the RAM has been implemented in such a way that it can hold information that is being processed by the CPU. And the main memory is also associated with processor. So moving instructions and information in and out of the processor is extremely fast. So if you have a memory that is not quite efficient in terms of data retrieval and access, then that is where they will say that your memory is very slow. And in the computing system, we have DDR3, the DDR4, and the rest. And all of them, they have Arthur, can you mute yourself? And all
Sorry,
of
sir.
these one, DDR2 and 3 and 4 are basically designed in such a way to effectively provide information whenever the CPU needs them. Is that clear? So this is how the memory basically works on the left of the diagram or the screen. So we have registers, we have the cache, we have the main memory, electronic disk, magnetic disk, optical disk, and then magnetic tapes. And this is basically to tell us how the information is being read from the main memory. So we have the registers, we have the cache, and then we have the main memory as well. And the others also follows. And as we all know, the main memory, which is the random access memory, is very volatile. You lose power, it loses its data. All right, so let's look at in multi-programming computer, the operating system resides in part of the memory, and the rest is used by multi-processors. And the activity or the task of subdividing memory among different processes is what we call the memory management. And that is what we will be talking about today. The task of subdividing the memory among different processes called the memory management. And so if you have more like 6 processes that are running within the computer system, how can we manage the memory in such a way that those that needs it gets it, and those done with their processes leaves? How do we, let's say the space so that other process can also come in and then get executed. And by definition, memory management is a method in the OS system to manage operations between main memory and disk during program or process execution. And one of the main aim of this memory management is to achieve efficient utilization of the memory. As I said earlier, process that does not need a memory is not allocated memory. That is especially those that are done executing, they ought to leave the memory and make room for others to also come in when necessary. And these are some of the reasons why those who design the operating systems actually, implemented the memory management within it. So it is able to allocate and deallocate memory before and after execution. So as soon as the program is requested to be executed by the CPU, the OS allocates memory for it, and then either in the waiting state or ready state for execution, depending on the state. If you want input output and it is not available. And then also it helps to keep track of used memory space by processes. This is very important because when the memory space is full and the user initiates an instruction, it's very important for you to give a feedback to the user that you have less memory or you don't have enough memory to execute the process, to make the user aware of what has happened within the internal system. This is one of the reasons why memory management was implemented in the OS. And then also to minimize fragmentation issues, to properly utilize the main memory, and to maintain data integrity while execution of the process. And then also read on logical and physical address spaces as well. So these are the reason why memory management is required. Now let's look at swapping in the process. When a process is being executed or a program is being executed, that is where we get the swap. That is where we get the swap. And in just a minute, the image just distracted the text. All right, so when a process is executed, it must have residence in the memory. And then swapping is the process of swapping process temporarily into a secondary memory from the main memory, which is fast compared to the secondary memory. So what we are talking about here, if a process is being executed and it literally needs some input output, then we need to swap their position. That is, in the process of termination, for it to wait or go to the waiting state or ready state, so that others that have the privilege or all the resources available to execute will now move on and execute or run. So the swapping allows more processes to be run and can be fit into memory at one time. So the diagram we are seeing here is the simple swap process. And then we have the secondary memory, and then we have the main memory. And then we have the operating system. Please, can you see the screen?
Yes, sir.
Yes, sir.
All right. I want to annotate. So we have the operating system over here. Then we have the user space, and then we have the secondary storage. Right. So whenever there's a process in here, and then in the user space, then the process will be swapped. So as soon as the process 2 moves to the user space, then this one will be swapped into the secondary memory. And man, the user space has the main memory. So as soon as it moves from the secondary storage up to the user space, that means the program is ready to be executed, and then it starts the execution process. Is that clear?
Sir, please come again.
All right, so what I'm saying is that we have what we call the swapping in the operating system during the memory management, right? And when we talk about swapping, is a process of more like changing or swapping a process temporarily into a secondary memory. The process has not finished executing, but then it needs some other resources to continue with the process, right? So it's very important not to keep it in the main memory to occupy space just like that. So to manage the space in the main memory, it is required that we swap a program or a process that is ready to another process that is not ready. So if it is ready or is executing and then it's waiting for some input output or some instruction, and instruction is not given, the OS will have to now swap that process in the main memory to some other one that is in a secondary memory waiting for execution, right? And this secondary memory might
Yes,
not
sir.
necessarily be might not necessarily be the hard disk, but it could be either the register or the cache, because the cache stores temporary information or resource or process that has run, let me say, they finished executing not quite long ago. So the cache will store those ones, or frequently executed program. That is where those ones are going to be. So literally it will move into that secondary storage, or with some other one that is ready to be executed, comes into the main memory and then starts running, just not to occupy space in the main memory while it is not being executed, right? So an example could be when you open Microsoft Word and you leave it there for a very long time, because there are no interactions. The OS will have to now switch or swap it with some other process that is running to make room for the memory and allocate the memory properly to other resources that needs it. So that is what the swapping basically does. Just like how we also swap stuff. If we realize that this is not efficient or this is not being utilized properly, we can just swap it with some other one, and then that is how it goes. Now let's look at how the OS manages free memory. And when the memory is assigned dynamically, the OS has the responsibility to manage it. When the memory is assigned dynamically, it is the duty of the OS to manage it. And let's understand it. How can the OS manage memory usage? If you have any idea, you can let us know. So, but then before, let's understand that when the memory is assigned dynamically, the OS will have to manage it, obviously. So if you have any ideas to how that can be done, you can help us understand it. All right, so if no idea, let's continue. So there are two ways to track the use of memory within the operating system. And one of them is the bitmaps. The second one is freeze, and the bitmap all the allocation states or status of blocks or sectors on a storage device, such as a hard disk or a file system. So that is one of the ways the OS keep track of memory usage. So it's able to keep track of the allocation states or status of blocks or sectors on storage devices, such as a hard disk or a file system. And being able to track the allocation status, it basically means that if the file has or the process has ended successfully, then it will notice the status and probably just deallocate the memory from the system. Then also we have the free list, which is another method of managing available disk space in an operating system. So instead of using the bitmap, the free list basically maintains a linked list of available blocks or sectors. So this is how the linked list really works. So when the processes are being executed, they are kind of linked to each other with what we call a pointer. So one of them, if the first process is being executed and then the next one comes in, is going to be linked to it based on what we call a pointer. And then if you do data structures, you get to linked list, you understand how this basically works. But you have to understand that the free list basically uses a linked list data structure of the available blocks or sectors to be able to manage the memory that we have. And or it can also use the bitmaps to do that. Please, are we clear? And then if you want more information, you can follow this link and then you get more information over there. So just notice that the two ways to manage memory is the bitmap and then the free list as well. All right. Now let's look at the memory management using the bitmaps. And I believe all of us know bitmap. Those of us who are into what's the name?
No, sir.
Graphics.
Please, we don't know.
No, sir.
You don't know bitmaps?
No, sir.
Sir.
Clifford, do you know bitmaps? All right, so let's continue. After that, you understand. So memory in a bitmap is divided into allocation units. Corresponding to each allocation unit is a bit in the bitmap. So the bitmap is more like a map which contains bits, right? With value 0 if the unit is free, and with value 1 if the unit is occupied. So mostly the bitmap is a map, or let me say a structure that has the bit values in them. So 0 and 1, 0 and 1, 0 and 1 in that sequence. Please, are we clear? And then these zeros and ones basically represent the status of the memory block. Then that's what I said earlier, whether it is free or is occupied. So if it is free, then the bitmap value is going to be 0. If it is occupied, then it's going to be 1 inside the memory. Please, are we clear? All right, so I think I have examples, so we'll see and then understand it quite well. All right, so this is the example that I was talking about earlier. So figure A, a part of memory with 5 processes and 3 holes. The tick marks show the memory allocation units. The shaded region 0 in the bitmap and 3 in the corresponding bitmap. So this is what we have. So this is the more like the CPU that is executing the process, and then we have the processes all over here. This is a bitmap that we have. So this map that we have built from this particular place inside the memory to show if the place is free or it's not free. Please, are we clear? And in the bitmap, those that are ones basically means that that space in the memory is not free. Those that are 0 means that it is free.
Oh, okay.
Please, are we following here? So this is how the bitmap is basically built. So wherever you find a 0, it means that memory space is available, and then you can assign it or allocate information or processes to start running over there. However, if it is 1, the CPU knows that no, this place is occupied, and then I have to search for different places to do that. All right, Clifford.
Sir, my network was challenging, but someone just drew my attention that I was called or something like that.
Yeah, I was asking whether you know what a bit.
Hello?
Yeah, so I was asking whether you know what a
Hello? A bitmap.
bitmap.
Hello? Sir, did you say a bitmap?
Yeah, bitmap.
Bitmap. Maybe I can explain in relation to designs, maybe graphic designs. Hello?
Right, that's fine. That's fine. I think we have it now.
Maybe like in okay.
Yes, thank you so much. So as I was saying, we have, I mean, these words can be interrelated in different fields. So in graphic design, we have bitmap as well. And then in OS, we have bitmaps also. But in the OS bitmap, it is used to manage memory spaces, to know that which space is available and which space is free so that it can allocate resources to it. And as I was saying, if this is a process block, there is horizontal rectangle here. If this rectangle is a process block or the CPU in the CPU or memory, how do we know that this place is free and then we can assign some process to it or allocate process to run in there. Then we have to build the bitmap to be able to know that, and that is how the CPU does. And as I was saying earlier, wherever there is a 1, the CPU knows that that place is not free. Wherever there is 0, that means the place is free. So from the diagram here, we could say that this place in memory is free. We can allocate resources or processes to start running. This same applies here. It is not free, and then we can't allocate any space at that particular place. So that is how the bitmap is used to manage the memory. Please, are we clear? So now from the previous figure we saw earlier, we had this bitmap value 111 up to the last 3 zeros. So position 1 through 5 are occupied. Similarly, position 6 through 8 are free. Position 9 to 16 are occupied. Position 17 and 18 are occupied in that order. Then the operating system will know that no, this place is occupied. Then we have to move on to some other places also. Now let's look at the memory management with the free list. Mind you, put this in mind that the memory management using the free list uses the linked list data structure. Instead of building a bitmap, it uses linked list to be able to know which place is free and which other place is not free. Please, I hope we are following. Any question? Do we have any question to ask? Or we are all okay?
It seems someone found this out.
Please, you can ask the question. Clifford and Atta Abdul Hafiz. Abdul Hafiz, your hand is up. All right, so let's move on and talk about the memory management with free list. So one of the ways to also keep track of memory is to maintain a linked list of allocated and free memory segments, where a segment is either a process or a hole between 2 processes. So this is a track of the memory through the linked list allocation. Let me position there, right? So all right, so we have it on the diagram here. The same diagram we use the bitmap, represented use the bitmap. This is also what we have. So as I said earlier, each of the space or each of the free memory segment or memory segments is linked to the previous one, right? So this is what we have. So we have this memory segment, we have this memory segment as well, and all of these rectangles with the values in them are memory segments in them, and each of them are linked to each other using these arrows. So this is how a linked list data structure basically works, right? Up to here, and then up to the last one over here. And then we have the various labels as H, which is the whole we spoke about earlier. We have the start at 18 and the length as 2. And each of the P's happen to be the process in there, right? So those that have processes in them basically means that they are running, and therefore there's no space in that particular segment. And places where they have a hole, it means that that place is more like empty, and then you can move further and can allocate processes to it. So these segments are literally free. This is H, which represent a whole, and this one as well. And these are processes that are running. Those blocks that has P at the starting point. And that means that at that particular place, it is not free, and therefore you can't allocate spaces to that. However, the other ones, you can allocate spaces to them, and then execution will start from there. Please, are we clear?
Yes, sir.
All right, so notice two things, the bitmap and then the free list. All right, so from the figure we saw earlier, it shows 5 processes and 3 hosts. So the thick mark shows the memory allocation unit. The shaded region, which is 0 in the bitmap, and free as well. The same information as listed in this particular reference that you can look for. So from the previous figure, each list entry specifies H, which is a whole, P, which is a process, starting address, length, and then pointer to the next available item that we have. All right, so let us continue with the free list. So how should this list be managed when a process terminates or is swapped out? Please, anybody to help us. This is the linked list. So if a process is terminated or is swapped out, how should it be managed? Anybody? Hey, nobody to help us. All right, so in the previous example, as we saw earlier from the segment list, which is kept in sorted by addresses, and the termination process normally has 2 neighbors. This is true except when it is at the very top or bottom of the memory. So neighbors may be either processing or holes, leading to the combinations, leading to 4 combinations over here. And these are the 4 combinations that we can talk about and related to how to manage if the memory is swapped out or it's terminated. So before the termination, this is the block, memory block we have, or the segment block we have, A, X, and B. So after the termination, this particular block A becomes this. Please, are we clear? This particular block A becomes this after the termination. And also, after the termination, this okay, so after the termination, this one also becomes, this B also becomes this one here. And then the third one becomes this. And finally, this one becomes this one over here. Please, do you understand how it really works?
So please kindly go over it again for us.
All right, so what I'm saying is that before the process X terminates, before the process X terminates, this is how it is earlier. Right? This is how it is. And after it terminates, this is how it is going to be. That is to say that this particular place is going to be, I mean, let me say, if it is bit map we are talking about, this place is going to be 00000 because we have terminated the process X, and therefore we are releasing or deallocating the memory space, representing them with 0000. And then since this is a memory block or a segment in a list form, we cannot use the 00 to represent. So we just have to use any symbol at all to represent that this particular block is empty. So this is the execution block. And then this is going to be how it will look like if it terminates. I hope it's clear. And now also for process block B, this is where the X is. So now if X terminates, then it means that this is a free memory space. Then this is also going to be a free memory space. So all of them are going to be merged together to get this free memory space.
Oh, okay.
Please, are we clear? All right.
Yes.
And also,
Yes,
C. Right, this is also C. And this is free memory space. And this is the process executing. So before it terminates, we have to deallocate the memory space from this place and then merge it together. Now we have this one over here. The same way applies to this as well. All of these ones are empty and this is also empty. So merging them together means we have a full memory block that is free for us. Transport.
So, sir,
Okay.
Yes, sir. Sir, can we link this to partition of a hard disk?
I don't really want to say that, but then the same ideas that is being used over there to merge those spaces are what the memory also use. Right. So if there are no spaces somewhere, you can merge them together, and then but then this one, a process has to stop before you deallocate the memory and then merge them together with other memories that are not being used. Remember, this is in the RAM, not the secondary storage. Ivano.
yes, sir. So please, I also wanted to find out the area marked A and B. For example, the very first one. Does it mean that there is something happening in those areas? What is occupying those areas? The marked place with.
So these are what should I say? Let me see if I'll get them from this slide. I wanted to say these are just numbers here. These are numbers over there. These are just numbers to show, I mean, the process block and where the actual execution is actually happening.
Okay.
Right.
Okay. Okay.
All right.
So it means that the areas marked A and B,
yeah,
those nothing is currently happening there, right? It's only the area
no
marked with X that is
X. Yes. So even ideally we could say that the A and the B could hold some threads or some spawn instructions, but the X itself happens to be exactly
the parent.
Yes.
Okay. Okay, I get it.
All right. Yeah, but then mind you, we said earlier that as soon as you switch off or you terminate the parent, the spawn and processes will have to go off. But then if
Yes.
the process can run on its own, it can still be there. I think that is why these ones are still here after even terminating X. Because you can execute a process, you close the process, and then others will still be running, though they were initiated from the parent process.
Yeah, so please give me an example that you can cite for us.
Example. Let's go. Maybe we see examples over there. I don't have any clear cut example here for you.
Okay.
All right.
Thank
you. Right, you're welcome. So figure 8, updating the list requires replacing a P with
I think I can help with the example if it's valid.
Okay.
Yeah,
Yeah,
so
give me, let's see if it's valid.
those who use Photoshop software, you can see that after closing the program, and on the tax bar, the tax manager, you still see the Adobe Creative Cloud content manager still running, even if the program is closed.
All right. Thank you so much. So that can be an example. Some of the program, when you even switch them off and you want to completely shut them down, you have to go to the task manager and kill it yourself. If not, or end the task. If not, it won't stop. Because probably some thread or span are running to help some other programs also be stable. Right?
Yes, sir. Thank you.
All right, so let's look at this one. So for figure A, updating the list requires replacing P with H. And then the P is the process and H is the whole. And then for figure B and C, 2 entries are merged together as one. That is what we have here. And then this one. And then finally, figure D, 3 entries are merged together to form the entire 3 memory block. Without we are clear. All right, so let's talk about virtual memory. I think our second lecture, someone mentioned virtual memory. And a person repeats so that we move on. What is a virtual memory? Please, anybody? Virtual memory. Nobody's here to help us. All right, Clifford.
I think the virtual memory is a memory management technique that allows the computer to use its part of its secondary storage as an extension of the RAM. So when it realizes that the RAM is getting full, then it picks part of the secondary storage, which normally is a hard drive, and then creates a virtual memory to serve as an extension of the RAM.
Okay. I think we are done with virtual memories because he just explained everything. Right. So thank you so much, Clifford. So that is very true. So whenever you start the execution process of any application in your computer system, the operating system, one of the techniques it's used to manage the memory is to give, let me say, an illusion of a large and continuous memory space to each of the process that you have started. And this happens even if the computer physical RAM is even small, right? And as Clifford just said, how it basically works is that the main memory will have to be available, and then also it uses part of the secondary storage as well. And in most cases, secondary storage are mostly used as backup memory. So these days, if you open Microsoft Word and your machine goes off and you haven't saved the information, it is very likely that you'll still get back to where you stopped or where you got to, and then the Word went off. So purposefully, this is used for backup stuff. Please, are we clear? So
Yes,
basically, the computer addresses more memory than the amount physical installed space to the process. And then this extra memory is called a virtual memory. And it's a section of a hard disk that is set up to emulate the functionalities of the RAM. And as I said earlier, it is mostly used for purposes of backup. Abudu, your hand is up.
Yes, sir. So please, I think if you can tell Ansan Samuel to mute his device, because
all right, so
he's giving some.
Please, if you are not asking a question or maybe saying something, just mute yourself so that we can move smoothly. All right, so this extra memory that is given is what we call the virtual memory, right? And as Clifford said, it is a section of the hard disk that is set up to emulate the computer's RAM. I think most of these new machines that are being shipped in have these capabilities. Earlier on, there wasn't anything like that. And as I gave an example to Microsoft Word, if you are working with it and the machine goes off, it is very likely that you come back to see the same place you left. That is where you're going to see. And in most cases, you have this extension added to it as auto recovery or whatever it is. That is the backup I was talking about. And one thing you have to notice is that the virtual memory uses both the hardware and software to enable a computer to compensate for the physical storage or shortages that I'm talking about. And it helps to temporarily transfer data from random access memory to the disk storage, which basically helps to map chunks of memory to disk files, which enables the computer to treat the secondary memory as though it were the main memory. But you have to realize that this virtual memory in some cases is very much slower because you have to now fetch from the dormant memory and now more like put it into the active memory, which is the RAM, and then the process will start. That is quite slower than compared to the file being just picked from the main memory and then start execution. Is any question? So the virtual memory, as we said earlier, is a management system that uses both the hardware and the software. In the process, it maps logical addresses to physical addresses using memory management units. So in the operating system, we have the MMU that is used to map the logical addresses to the physical addresses. So when the RAM space is needed for other tasks, data can be swapped from RAM to the virtual memory stored on the disk. And then this swapping process can slow down performance, making more RAM desirable for better computing performances. And as I said earlier, that is what we're talking about. So fetching from the secondary storage through the RAM to the CPU is a very long process compared to fetching from the RAM and then moving on to the CPU. However, it enables efficient use of limited RAM resources by temporarily storing data on the hard disk that we have on our system. But ideally, if you're buying a machine, get appropriate RAM size or memory size. You have to really depend on the virtual memories for any other thing. So these are some of the situations where we can utilize the virtual memory. So when the entire program is not required to be loaded fully into the main memory, that is one of the ways. And user-written error handling routines are used only when an error occurs in the data or computation. So if you execute the program, it is not all the instructions that are going to be loaded onto the RAM, because some of them will need to be more like triggered when something happens. And if you load all of them into there, they are going to just occupy space. And if there's no error, it literally means that the space is being wasted over there. And then also certain options and features of a program may be used rarely. And so virtual memory is very much important. So those features that are used rarely are practically stored in the virtual memory, whilst those that are frequently accessed will be in the RAM being executed. And then also many tables are assigned a fixed amount of address space, even though only a small amount of the table is actually used. And the ability to execute a program that is only partial in memory would counter many benefits as well. So this is how the virtual memory can work. Please, any question? Any question? All right, so we have the diagram here. I think it's about missing some information. And then the virtual memory is commonly implemented by what we call the demand paging. And a demand paging is a system, it's quite similar to paging system with swapping, where processes reside in secondary memory and pages are loaded only on demand, not in advance. So that is what the demand paging basically looks like. So the pages are stored in a secondary storage, and then as at when the demand requires that we load those those pages, then we load them onto the system. And this is the same process that the virtual memory really works. And this is a diagram that is to show the demand paging. So we have the main memory over here as the first block. This is the main memory, and we have two processes in it that are running. Right, and then we have also the secondary memory over here. right? And so now we could say that this process one has this virtual memory, which stores its information over here. And similarly, process 2 also has this virtual memory as well. So as this information here is needed, then it goes into the memory for execution. So sometimes error handling might not be loaded fully onto the RAM. So they can be kept in here. And therefore, if there's any error that occurs, that is, it's needed to be loaded onto the user. So the user will see the error that he or she is encountering. So it will now be loaded from this virtual memory onto the RAM, and then it will be executed for the user to see as a prompt or whatever that has been configured for them to see. Please, are we clear?
Yes, sir.
All right, so when a page or when a program tries to access a page that is not currently in the main memory because it was previously swapped out, it triggers a page fault, and then the page fault causes the processor to hand control over to the operating system, which is responsible for bringing the required page back into the main memory from the secondary storage like a disk or whatever it is that's the virtual memory is residing on. And these are some of the advantages that we can talk about. So it provides large virtual memory size, and then it is more efficient to use. It promotes more efficient use of memory as well. So large virtual memory and then more efficient use of memory as well, because not all the program's instructions are loaded onto the main memory just to occupy space, but then those that are frequently executed are what will be loaded onto the main memory for execution. And that's at when the rarely used processors are needed. It will now be called in from the virtual memory. And this is one disadvantage that we can talk about. The number of tables and the amount of process overhead for handling page interruptions are greater than in case of a simple page management technique. So this is required. This is the case if you have so many pages to be read from the memory onto the secondary memory onto the main memory, or you have so many pages like we saw over here. So if you are supposed to swap in a lot of pages from the virtual memory here, that is where you can get the performance overhead that we are talking about. But then if it's just a simple page that you want to swap in, it becomes quite easy. But then if it's multiple or more of them, then you're likely to get this processors overhead as well. All right, so let's talk about page replacement algorithms. And so this page replacement algorithm are the technique used when an operating system decides which memory page to swap out and write to disk when a page of memory needs to be allocated. So when the process and holes are kept on a list sorted by address, we realize several of the algorithms can be used to allocate memory for creating a space and then also swapping an existing process from the disk. And then some of the algorithms include the first fit, next fit, and then the best fit. So basically, a page replacement algorithm looks at limited information about accessing the page that provides or that is provided by the hardware and tries to select which page should replace to minimize the total number of pages misses or page misses. And in this process, we have to balance the cost of primary storage, the processor time of the algorithm itself. And one thing you have to notice is that there are a lot of these page replacement algorithms that you can go and look for. Please, any question on the page replacement algorithm? All right, please, you can ask the question. I think somebody's hands is up. Please, any question?
Hello, sir. Please, I'm not too clear about it.
The page replacement.
Yes, please.
All right, so when we talk about the page replacement, it is an algorithm that is used by the operating system, right, to decide which memory page to remove when a new page needs to be loaded into the memory. However, there's no free frame available. Right, so this is an algorithm from the computer, how it will be able to decide which memory page to remove. So you realize that in the RAM or in the RAM, all the pages that are available are being used by the operating system. I mean, by the processes that are running. But then there's a need for another page to be added or a new page to be loaded into memory. Right, so this is where the page replacement algorithm comes in. There are spaces, there are, let me say, pages that are running in the main memory. Just a minute. Okay, so there are pages that are running in here. However, the main memory is full. But then one of the process is requesting for a swapping of a page. And now all the pages that are available are now being in use. How will the algorithm make a choice of which page to remove from memory and then how it will bring in the new one?
Okay.
Please, are we following?
Yes, please.
All right, so that is what a page replacement algorithm basically does.
Okay, thank you, sir.
All right, and
Okay.
some of the popular algorithms that can be implemented in this scenario is going to be the FIFO. I don't know if you've heard of it before.
I believe are you referring to first in, first out?
Exactly. So that is one of the algorithms the essential annex up. So it is a duty the CPU to now decide to use either first in, first out operation or any other algorithm such as the most frequently used, least frequently used, least recently used, and all those algorithms. So whichever one you want to use, then depending on the implementation, the algorithm, I mean the operating system, that is what it's going to use. Please, are we clear? So just understand that the replacement algorithm means that there's no memory space in the main memory. However, one process is requesting for a page to be swapped in from the virtual memory. Now, how will the operating system be able to move one of the pages in which all of them are used and bring in the new one? And with that, as I said earlier, there are algorithms that the operating system might employ in this process. And one of them is the FIFO, the least recently used rather. And we have some of them on the screen that we can talk about, which is the first fit, the next fit, and the best fit. So let's talk about them more. So with the first fit, so if the OS get to this particular point, it has the choice to use the first fit, the best fit, and the rest. So for the first fits algorithm, it searches for the first free partition that is large enough to accommodate the process. Richard, your hand is up.
Yes, sir. Good afternoon, sir.
Good afternoon.
Please, you said something about the virtual memory.
Yeah.
I want to know for how long does, let's say, there is a process in progress and you have not saved it and the machine goes off due to maybe power outage or anything. For how long does it take for that document or process to be kept in the virtual memory before it is totally wiped out?
For that one, I can't really tell how long. I can't really tell how
because
long.
Let's say you are working on a project. You are working on a project.
Yeah.
You are working on a project and let's say light out.
Sir, can I come in?
I can. All right, I'm coming, Clifford. Hello. So I can't really give you a specific time. Clifford, just a minute.
Okay.
I cannot give you a specific time that the virtual memory will be deallocated. But then it also depends on, as you said earlier, the hardware and the software as well. So if the software you're using, is efficient to keep for a very long time, then you might come to find it. But I've witnessed a situation where I couldn't save the Word file. But in the following day, when I on the machine and opened one of my Word documents, the previous one I was working with also opened with my current, with up-to-date information in there. And then they were requesting me to auto-save my response. So yes, it depends on the software you're using and the hardware as well. All right,
okay, Clifford. So does that mean, sir, let me come again, sir.
All right.
Yeah, so does that mean that when the machine is prompting you to auto-save and you refuse to save it, does that mean that when you off it and come and you meet it again?
No, so it is implemented for system interrupt, not deliberate thing. So if you deliberately switch off the machine, that is your own problem. But then like power outage or something else, then it might save it for you. Those are what I've experienced. I haven't deliberately refused to save the file, like switch off my machine and come back and I see the result intact. No. I want to see the machine go off. And then when I on it again, I see all the information up to date for me.
Okay. Thank you, sir.
Yeah. All right. Clifford.
Sir, I think you have said most of what I wanted to say, but I have also had same experience even with Photoshop. Okay. Sometimes you do your designs to some level, you don't save it, and then the system goes off. Even if the machine lies down for even days before you power it on, you still get it. Once you open the software, it will still load that particular design for you. So sometimes, as you said, it's based on the software. But if you deliberately turn it off, I think with the Windows that we use nowadays, Windows 8, 9, 10 coming up. I think when you want to turn it off yourself, the system will prompt you that these files are or these programs are still running. Do you still want to turn it off? If you go in that direction there, I don't think it will save it for you.
All right, that's very true.
Because you
That's very
deliberately
true.
turn off the computer.
All right,
Exactly.
thank you.
All right, so these are mostly built in for, I mean, emergency purposes, not deliberate issues. All right, so when the computer faces or the OS faces this situation, it will have, as I said earlier, several options to choose, first in, first out, and all those stuff. So one of them is the first fit algorithm, and the first fit algorithm searches for the first free partition that is large enough to accommodate the process. So assuming that you want to swap in a page which is maybe 2 megabytes, it will search through the entire process, which page is having 2 megabytes space or 3 megabytes space. Then it will swap out that one and swap in your new page, and then you start running the process. So that is what the first fit basically does. So the memory manager scans the list until it finds a hole that is big enough, and the hole is then broken up into pieces, one for the process, one for the unused memory, except in the statistically unlikely case of an exact fit. So if there's no exact fit, that is mostly what happened. But I know that the first fit looks out for large enough memory that can accommodate the process, and then it swaps it in. Please, are we clear? So, for example, supposing we have the following memory partitions: 10 kilobyte, 20, 15, 25, and then 30 kilobyte. Now, a process requires 18 kilobytes of memory. So the operating system starts searching from the beginning and finds the first free partition of 20 kilobytes. It allocates the process to that partition and keeps the remaining 2 kilobytes as a free memory. Please, are we clear? Because the first one over here is 10, which is quite less than the memory space we need. So we move on to the next, which is 20, which is higher than what we need. So it picks that one and then it keeps the other one as free memory. All right, so let's move on to the best fits scenario. So the best fits algorithm searches for the smallest free partition that is large enough to accommodate the process. Mind you, the earlier one was the largest. This is the free partition that is large enough to accommodate the process. So for best fit, search the entire list from the beginning to end, and for the smallest hole, that is adequate. Rather than breaking up a big hole that might be needed later, hole that is close to the actual size needed, best match the request, the available hole. This is slower than the first fit, but the entire list must be searched every time. So we equally have an example over here. This is an example. We have the same kilobyte memory partition. Now a process requires 18 of memory. The operating system searches for the smallest free partition that is larger than the requested 18 kilobytes. And it first find a partition of 20 kilobytes. Allocate the process to the 1 kilobyte. We had 19. Then it is going to pick the 20 and look out for the 19. Because we are looking for the smallest, which can be requested space. That is the best fit scenario here. Please, are we clear? Now you usually have the best fit, which is the worst fit scenario. And the worst fit for the largest fit. Yakubu Mohammed. Yakubu Mohammed. Or Jacob. Jacob Mohammed, sorry.
Hello. Hello, sir.
You can hear you.
Sir, I'm confused with the example of first fit and then the best fits. The
Please, why are
20
you confused? Which of them?
kilometer. The example that you gave us 20 kilobytes as the first fits. For the first fits.
Yeah, so we are saying that for the first fits, it takes the largest value and the next largest value and then stores our process in there. And from here, the largest value is 20 kilobytes. So it picks that and then assign that to our process request, which is having 18 kilobytes.
Okay,
and
sir.
then the best fits also takes the least, as we saw here, smallest. And if you look at all of these ones, the smallest, although it is, we have 10, we have 15, but then all of them will not fit the process route. So the next one is 20, and then it takes that and assign a process to it. So I would say that if we had 19 kilobytes, then you would have skipped the 20 and take the 19 because that is the least.
Okay.
I mean, storage it needs, yeah. All right, so moving on, we have West Fit as well. And the West Fit algorithm, searches for the largest free partition and allocates the process to it. This algorithm is designed to leave the largest possible free partition for future use. And the reason why you are calling it West Fit is that it is taking up the largest space that we have. It is not optimizing the space. That is why we are calling it the West Fit. So works the same way as a first fit, except that keeps track of where it is whenever it finds a suitable hole. And next time it is called to find a hole, it starts search from the place where it left off last time, instead of always at the beginning as first fit does. Please, are we clear? So let's look at this example over here. So we have the same memory as previous, 10 kilobyte, 20 kilobyte, 15 kilobyte, up to 30 kilobyte. Now the process that is being requested or want to execute needs 18 kilobytes of memory. Instead of it optimizing the space and choosing the least, it is going for the greatest one or the largest space that we have. So the operating system will search for the largest free partition, which is 30 kilobytes. It allocates the process to that partition and keeps the remaining 12 kilobytes as free memory. Meanwhile, the other ones were keeping 2 as free memory. Please, are we clear? Any question? All right, let's look at some pros and cons associated with this particular first fits and the rest. But the first fit is faster and simple to implement, making it more commonly used algorithm. However, it can suffer from external fragmentation where small free partitions are left between allocated partitions. Because there are not large enough spaces or partitions left. That is why we are saying that there could be fragmentations within the process. And then for the best fit, reduces external fragmentation by allocating processes to the smallest free partition. But then it requires more time to search for the appropriate partition. And for the worst case, it it reduces external fragmentation by leaving the largest pre-partition, but it can lead to inefficient use of memory, as I just said earlier. That is what we call it the worst fit. Please, are we clear? Do we have any questions to ask? All right. Please ask the question.
I wanted to find out this memory management. I think
okay,
it is something that the system itself controls it. Do we have any control over it as users?
No, that is the internal workings of the operating system.
Okay.
Those are the internal workings of the operating system. Yeah, I mean, you, the user, don't have control over it. So the only control you probably have is if the system prompts you that you have less RAM or memory, then you may have to install a new upgraded version as well. But in its management, you don't have much process activities to do. Yeah.
Thank you very much.
All right, so let's move on and talk about memory segmentation. But then what is segmentation? Is anybody okay? Segmentation. Abdul Hafiz.
Segmentation simply means dividing of something or putting something into divisions.
All right, thank you so much. Anybody else?
Yeah, sir, please, can I talk?
Yes, come in.
My understanding is having a division and dividing something into various groups so that
okay,
one that will be applicable, you make use of it.
Okay, all right. Richard, your hand is still up. You want to say something?
Yeah, I think you were asking a question on the segmentation. Let me also input my small. I think is a breaking down of or partitioning something into smaller units or sectors.
Okay, thank you so much. Thank you so much. Atta Abdul Hafiz. Chris, your hand is up.
Sir.
All right, tell us something.
What I'm trying to say is segmentation, my understanding, has to do with putting something into these various positions. For instance, you try to divide something into the various groups.
Okay. All right, you're welcome. Thank you too. Chris.
Yes, sir. I think segmentation is dividing computer networks into sub-networks to improve its security, risks, and performance.
All right, thank you so much. So when we go to networking, that is very, very appropriate, right? And then segmentation too is more like all that you said is true and correct. Clifford, you want to add something?
Yes, I think they've said it all, but relating to the memory, I think segmentation is all about dividing the memory into logical units.
Okay. All right, thank you so much. So that is correct as well. So basically, segmentation is one of the memory management technique, in which the memory is divided into varied size parts or into logical units, as Clifford just said. And each of the part is known as the segment. And each of the segment can be allocated to a process that is being executed. And as you all know, the program is not just made up of the block, but naturally, those of you who write computer program, you know that it's made up of codes, it's made up of data structure, it's made up of stack, it's made up of heap, and many other segments. And for the code happens to be the instructions, the data structure or data segment has to be the global variables, the static variables that we declare, and some other functions that we have. So these are the divisions that we can actually get. So you divide, or you logically divide the memory to hold up any of those sub component within the process that you have started. Right, so that is what memory management, memory segmentation is all about. That is one of the techniques that we have, and you have to notice that it is used to divide the memory into logical parts, which are mostly in varied size. And then each of these parts happens to be called a segment. And each of the segments can be allocated to a process or a program that is in execution. And then the segment table contains mainly two pieces of information about the segment. So in the operating system, whenever the segmentation to manage memory, we have what we call the segment table that is created, I don't know whether virtually here. And in that, we have what we call the base and the limits are the two most important piece of information that we can find. And the base basically is the base address of the segment. And the limit happens to be the length of the segment. So who can tell me what the base or the base address mean? Or what would the base address or the base actually do? Any all right, so actually there are three, but the main two ones are the base and then the limit. But the second one is what we call the segment number, which is basically used to identify the segments. So we have the segment number, the base, and then the limits. The segment number identifies the segments. The base is the base address of the segment, and the limit is the length of the segment. So the base address, what it basically does, it helps the operating system to be able to locate exactly where each of the segment is within the computing space. And the limits also talk about the length of the segment or the size. So in the process, assuming that you have five segments, and each of them is below, let's say 25 kilobytes. It's only one of them that is above 25 kilobytes, let's say 35 kilobytes. And then there is a process that wants to be executed, and that one has a space of 30 kilobytes. Obviously, you have to look for all the segment addresses, and in the process, you check for the length of the address, which one is suitable for this process to run on. Please, are we clear with this? So the base will help the OS to locate where the segment is in memory, and then also the limit will help the OS to be able to assign various processes that want to be executed onto it. Precious, your hand is up.
Sir.
Talk to us.
Segment. Yes, sir. Please, what's the difference between the segmentation and the defragmentation?
Oh, okay. Don't worry, talk about that. I'll answer the question, don't worry. Abdul Hafiz.
Okay.
Abdul Hafiz.
So earlier on, you were giving a definition on the base and the limit, but I didn't get it clearly. Please, can you go over again?
Okay, so Precious, when we talk about segmentation, we are basically dividing something into varied sizes, right? And when we talk about defragmentation, we are basically reorganizing the scattered blocks of data on the storage device. So in most cases, when you what's the name? When you I've forgotten the name, but I'll talk about it later on when I remember. But then note that defragmentation is a process we use to organize data blocks on storage devices so that the related pieces of data are stored close together. And then the segmentation is just dividing memory into variable sizes or varied sizes. Please, I hope it's clear.
Sir, can I?
Yes, sir. Thank you.
Oh, okay.
Okay. All right, Clifford.
I wanted to just give a typical example in real life.
Okay.
So she should use her room as a storage device. There are ways that she has divided parts of the room where she keeps her bed, where she keeps her chairs, her books, and all that. So that one has to do with the segmentation. She has divided parts of the room and decide to store what at what section, what at what section.
Yeah.
So that is where the segmentation comes in. But with the defragmentation, you realize that sometimes at the point in time, the manner in which you initially arrange the things in your room, in one way or the other, you have placed them somehow in the room which didn't fit the initial arrangement. So you have to pick them back and then arrange them to make sure that related items are placed at the same segments. That is where defragmentation comes in.
All right. Thank you so much, Clifford. Thank you so much. And in real life situation, especially if you install Windows and you do what's the name partitioning here for one of the, you separate the disks into two, and later on you don't defragment, you are not going to see that particular disk space on your device unless you go back to the system and then do the defragmentation, because at that point in time all the data blocks are scattered around and they don't have any sort of identity. So you have to go back and now defragment the data to make sure they all come together and have an identity so that you can now see and store your information onto it. Yeah, so someone was asking about the base and then the limit. So the base stores the base address of the segment that is in memory. And also the limits is the length of the segment. And I was saying that the base helps the OS to locate where that particular segment is. And the limit gives it space to be able to assign processes that want to run to that particular segment. And I give example as if let's say that a segment in the machine is 3 or 5, and all the 5 except one is above 35. And now a process wants to start executing, and the process requires 30 kilobyte space. Then it will have to check the limit of all the segments that are available, which of them has the highest space that can accommodate the process, which has 30 kilobytes, and then it assigns it to it. So that is the base and then the limit. But I said there's another one, which is a segment number as well. Is any other question? All right, so let's continue. So we have, just a moment, we have some types of segmentation as well. So we have the virtual segmentation, and we have the simple segmentation. So the virtual segmentation, each process is divided into number of segments. But then the segmentation is not done all at once. That is the virtual segmentation. The segmentation is done, but not all at once. That is the virtual memory segmentation. Then we have the simple segmentation, where each process is divided into a number of segments, all of which are loaded into memory at runtime, though not necessarily contiguous. So we have the virtual segmentation, where each process is divided into a number of segments, but the segmentation is not done all at once. And also we have the simple segmentation, where each process is divided into segments, all of which are loaded into memory at runtime, though it doesn't necessarily mean that they should be contiguous. So that is some type of segmentation we can talk about. And let's try to understand what we have on this particular diagram. So this is a logical view of, let's consider the diagram, please. This is a logical view of segmentation. And we have the address, logical address space, which is this one here. And then we have the segment table. Mind you, I said earlier, whenever you create a segment is created, it also creates a virtual table, which is called a segment table, which is what we have here. And a segment table has a base address, we said earlier, and also the limit. So this limit could be in kilobyte, depending on the OS implementation, or probably megabyte as well. And this is also the physical address space that we have as well. And then for the physical address space, we have segment 0, we have segment 1, segment 2, segment 4, and then segment 3. However, in the logical address space, this is how the segments are being represented. Please, are we clear?
Yes, sir.
So let's look at some advantages of segmentation. So whenever we implement segmentation, one advantage is that there's no internal fragmentation. There's no internal fragmentation that after that we need to defragment within the operating system. So as soon as the OS creates the segmentation, there's nothing like fragmentation in there. And then also the average size is larger than the actual page size. The size of larger than the actual page size. And then also we have less overhead as well. And it is easy to relocate segments than entire address space. It is easy for us to relocate the segments compared to relocating the entire address space. And then also the segment table that is being created is of lesser size as compared to the page table in pagination. So these are some of the advantages or why it is very important that segmentation was implemented in the operating system. Now let's talk about some disadvantages, and if there are no questions, we can close. So you can have external fragmentations, and it is difficult to allocate contiguous memory to vary size partitions. So if we want to allocate contiguous memory, that is memories that follows each other, it is quite difficult to do that when we are talking about varied size partitions, which are mostly used in the segmentation process. And then also it's quite costly memory management algorithm. The memory management algorithm is quite costly, especially when we go to the best fit and all those stuffs. It becomes very difficult for the system to manage those ones. So these are some 3 disadvantages of segmentation, but I think there could be more. So at your free or leisure time, you could just explore and try to understand more on that. Is any question? Any question on memory management, segmentation, and any others? All right, Clifford, ask the question after that. Abdul.
So when I raised my hand earlier, I forgot to lower it. I was riding, that's why.
Oh, okay. Abdul. Mohammed Jacob.
Yes, sir. Please, is there any disadvantages of segmentation, memory segmentation?
Is there any disadvantages of memory segmentation?
Yes,
I think that's what you just saw right now. So this is one of them. Or these are 3 of them.
Okay, sir.
Yeah.
I see. Thank you, sir.
Okay.
Thank you.
Please, any other question? Abraham.
Okay, sir. I actually don't have a question, but from the first slide, how the definition of memory, I think memory, it's a noun, a name. So, but it was defined as if it's a verb in the first slide. If we can go back to that.
Oh, really? Let me see. Yeah, this one.
No, the definition, yes. Yes, so memory is a collection of data. So it's acting like it's a verb, it's a doing word be. So I think it should be maybe whether a device or help us. Uh-huh.
So the term memory can be defined as a collection of data. Can you?
So can we say that it's a part of the computer or a device that is responsible for collecting data and then the rest of the meaning?
Okay.
I think there's
Understand
nothing
where
wrong with the collection of data. It's also a noun.
Yes, please, I'm not
No,
an
it is
English
saying that
teacher.
memory can be. Sorry.
All right, so don't worry, you
For
go on.
instance, a collection of shoes.
Let him finish before.
Okay, but I think that it's saying that memory is the term. Memory. The term memory can be defined as collection of data. So it's acting like it's a verb.
Oh, okay, maybe there should have been a collection of data.
Even that is the verb. So maybe a device that is
So,
responsible
what do
for
you
collecting
propose?
data.
It can't be a verb. It can't be a verb.
Yeah, so
I don't
memory is not a verb. Memory is supposed to be a noun, an object, right? But in actual sense, these memories is made up of programs, data. I mean, it's a collection of data that is mostly in a specific format. That is why you can't just load your word as we see to the RAM. So the RAM has to convert this computer has to convert all your Word document into something that it understands. So in the memory itself is a collection of data or data structures in a specific format.
Okay.
I don't know if you get what I'm saying.
Yes, I'm trying to get another meaning.
So do you write computer programs?
No, sir.
Okay, so we have what we call variables and storage containers, right? And
But
these
sir,
memories are built.
sir,
Okay, Richard.
yeah. So sir, is it wrong to say it is a device in a computer for collection of data? Like
No,
being
it's not.
saying,
It's not
let's
wrong.
in a. Okay, okay, okay.
It's not wrong. It's
Okay.
not wrong.
Because
It's not wrong. But
oh,
it's not wrong. But then
But sir,
hello. Okay.
so when we limit it to be a device, how are you going to explain the virtual part of it?
No. I'm not saying he should limit to. He said, "Can he?" And I said, "Yes, we can do that."
And
You know
that's what I'm
this.
also confused
Oh,
about.
but ideally, when we are talking about memory, we somehow don't really talk much about the virtual stuff. So memory is
Okay.
memory, unless you want to extend it to virtual and then the others. But then you can equally say it's a device, and then you are good to go. Because even the virtual is extracted from the device, which is this secondary storage device. So, right. Abraham, your hand is up, and then Abdul Hafiz. All right, so technically, memory is more like a data structure that holds a collection of information in a specific format. So please, if you think this is more like a verb, you can refactor it in a way that sounds more like a noun, and then you present it in the exam when it comes. Thank you very much. Please, any other question?
Hello, sir.
All right.
Yeah.
So,
Please, can you share your slides in our WhatsApp group for us?
Yeah, I'm not there, but I have one of your colleagues' numbers. I'll send it to him and then you get it.
Okay, thank you, sir.
Okay.
Sir.
All right, talk to us.
Hello.
Hello.
Yes. Yeah. Concerning the memory thing, I think when you go to programming,
yeah,
there's nothing wrong with your definition. Because over there we say variable. When you take a variable, you say that it serves as a memory unit or a container that is used to or store data of different kinds.
Yes.
So you don't just need to limit it to a device like memory card or pen drive.
Exactly.
Yes.
All right. Thank you so much. But even let's look at the human brain. Is it an object? Is it a device? What is it? All right. So without any questions, we'll close and then continue tomorrow, next week. Abraham, your hand is up.
Oh, sir, sorry, I forgot.
All right. So then we will close here and then continue next week, hopefully. Thank you so much. And please just go over it. If you don't understand anything, yes, we can ask and then we'll try to verify. William Jr. All right, so I'll see you next week.
Sir, I have a question.
Okay.
So please, about the segmentation, the advantages.
Yeah.
You made a question about less overhead as an advantage of the segmentation. Please throw more light on that.
Less overhead. Just a minute. But please, do you understand what overhead is? Or do we understand what overhead is?
No. No, please.
Abdul Hafiz, your hand is still up. Do you want to answer the overhead? All right. So when we talk about overhead, it basically means that extra work or time or resources that a system requires to manage or perform a task. That is what we call overhead. So extra work, extra time, extra resources that is required to manage a task or perform a task. And in this sense, if there's segmentation, remember we said that whenever the segmentation is created, it saves into the memory and it has allocated spaces that is for it. So whenever you initiate another process, it will just go ahead, the OS will go ahead and then push that process onto the end of the segment and it will start to run. So instead of the system waiting for you to initiate the process, it will now go back and now start to create different memory all together, or memory block all together for the process you just initiated. It becomes less in the sense that the process block is already created, which is the segment you're talking about here. So all it needs is just push the process you want to initiate onto the next segmentation and then it starts operating. Instead of starting to create it from the ground, it is already there, so you just push it in there and then it starts the execution. I don't know if it's clear.
Yes.
No, okay. All right, so without any other questions, we can close and then meet next week. Thank you very much for your time.
You're welcome, sir. Crossfire, please, there's lies.
He's here to send. When he forward it, I will push it into the group.
Okay, sir.
Please, I have something to say.
Oh, sure.
Can I go ahead?
Yeah, listening.
You remember that when we were having the basic design and color psychology lecture,
Yeah.
when we were talking about recording of the lecture, someone said, I think the name was Victor, said he was a monitor, which means every lecture they get someone to join us to monitor. So let's be careful what we say when the lecture speakers.
They're asking maybe someone made an utterances which we couldn't get. What is it?
Pardon?
I was asking, like based on what you rightfully said, I mean, was there any utterances that was being said which maybe you
No. I'm
noticed?
just saying it for future sake, not now. We haven't said anything that way. I just want us to know that this is what they do. They get someone to join every lecture to monitor what is happening. So the lecturer may exit and that person has not exited yet. So we should mind our utterances or what we say whenever the lecturers exit. That's what I'm just trying to say.
Oh, okay.
Operating system.
Clifford,
Yes.
when are we meeting?
It's up to us.
Clifford, when are we meeting?
When do you want us to meet?
Clifford, you did Taddy.
When do you want us? Yeah, I
Oh, anytime that we agree. Let's find one time we then.
Clifford, you did Taddy.
Easy Taddy.
I say, then God bless you.
Clifford, then let's create a WhatsApp group so that we can
Clifford.
He has already created a WhatsApp group.
There's a WhatsApp group for Tadio.
Where do you stay?
I'm at Efiekuma.
Efiekuma?
Yeah.
You there at Ekuma school?
No, I teach for town, but I don't Efiekuma.
Hi, I will look at your house door.
No.
Because yeah. I will come for the the third page. I will link up for them.
Okay. Someone said hello.
Because the math. Hey, this mathematics thing, Charlie.
The maths, I get all in lecture videos. Should I put them on a Google Drive so that we can download?
We can download the also need guidance to solve. We can download. We also need guidance to solve.
If you download and you don't understand, click for it to
so that's why we can have a meeting.
First of all, if like let's say we are compiled everything.
Maybe if we can find some time within the weeks and then we meet face to face to have some discussion.
That's why we are saying let's meet.
I teach at Anaje. Okay. Yeah, I teach at Anaje. So like linking up. If we get a location, we can see how we make.
After the location, for instance, my school, we can have any of the classrooms.
Which is what school do you are?
It's at the Central Police Station in town.
What's the name?
Reverend Joyapeki. It's within the Central Assemblies of God Church.
Reverend what?
Joyapeki Memorial Baby School.
That's new to me.
Clifford, where do you stay at Efiekuma?
Oh, I'm just at the bus stop. I'm just at the bus stop.
Mr. Amo, where are you as well?
I'm at Piper, no.
Asking a question.
Okay, what about your school?
I'm at Wood Methodist. Wood Methodist.
That's
okay.
Yeah.
Yeah, you see, I remember your case, Mr. Amo.
Yeah.
I remember your case very well.
Okay, so how they let's end here and then we'll do the other discussions on our page on third party.
Okay.
All right,
Yeah.
thanks. Thank you very much.
Okay.
Hello, Clifford. Clifford.
Yeah, hello.
Just say hi on the platform so that I can have a conversation with you. Just say hi.
Is it in the WhatsApp group?
Yeah. You know, any of the WhatsApp group. Let's see, the one with all study
All
centers.
centers.
Yeah. Just
Okay.
say hi so that I can go. Thanks.
Okay. You're welcome.
The lecture ended.
Pardon? Oh, the lecture has ended.
The lecture ended.
Amana.
The class finished.
Okay, I'll do that. I don't know where we're going. We can send me the forward me. Material.
Mun kawo like ba mu fafasa ba shi da Monday. Shi na ta na roko can.